Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 74. It's on electric circuits. And when my father was younger, he used to work on the telegraph. And the telegraph is a simple electric circuit with a switch. And so you can run electricity through it, and you can make a click sound that you can hear on the other side. But that simple electric circuit is no different than all the circuits that we're going to find in an iPhone like this. And so a circuit, to understand what's going on, the two big things you should get are going to be the voltage and the current. So the voltage is going to be the potential difference in different parts of that circuit, and then the current is going to be the flow. So it's really the movement of electrons through the circuit. You should also be able to understand how different elements in a circuit behave. And those four elements in AP Physics you should understand are the electromotive force, like the battery, also the resistors, the capacitors, and finally the switches. You also should understand how these elements are hooked together. Are they hooked together in a series, or are they hooked together in a parallel circuit? And so this is what the circuit elements are going to look like. We've got the electromotive force. The nice thing about AP Physics is you don't have to deal with AC power. We're just going to be dealing with DC power. But you should be able to recognize what does a resistor look like, capacitor, switch, and then finally a wire is just going to be a straight line. Now, to understand what's going on in a circuit like this, you have to have an understanding of how circuits work. And if you know anything about a switch, you should know that nothing is going to happen because we have this switch down here open. But a lot of people don't understand really what's going on at the gut level in an electric circuit. And that's why analogies are really, really helpful. And so in this analogy, we're going to use water moving through pipes to represent the electric circuit. And so in this analogy, the battery is going to be represented by a pump. So that's going to be our EMF, or electromotive force. And so what we have is voltage. Voltage is going to be the potential difference. So if you just stick your hand here and compare that to the pressure right here, we're going to have more force here, or more potential difference across that. But we're just measuring how much potential energy there is. We're not measuring the actual movement of that water in this case, and that's going to be our current, or I, in an electric circuit. So how much water is actually moving is going to be the current. And those are different things, and they're going to behave differently in an electric circuit. So if we look at the other elements, a resistor is going to be anything that slows down the movement of that water. And then a capacitor is going to be something, it's almost like a dam. A dam you could think of where we have a plastic rubber sheet that goes across it. And so what it does is it stops current, so we can build up charge on that capacitor. And then a switch is anything where we can simply just turn the whole thing off so water can't flow. And so if you have this analogy of how each of these elements work, it really helps you to solve simple problems. And so let's use a PHET simulation to look at a simple circuit. So what we have right here is a battery, and if I hook up a voltmeter, you can see that we're going to have a potential difference of 9 volts across that battery. If we put an ammeter in here to measure the current, you can see that there's not going to be any current. Why is that? Well, you can see that we have essentially a switch up here, so it's not closed. And so when I close it, you can see there's a huge amount of current. What we really would have done at this point is we're shorting out that battery because all of that current is quickly moving through. And so let me kind of split that junction. And now let's put one of those first elements in. We're going to put a resistor in here. Remember, that's going to slow the movement of that current. And let's say that this is a 10 ohm resistor. So could you figure out, before we connect that resistor into the circuit, could you figure out what's going to be the current in the circuit? Well, remember, Ohm's law is pretty simple. All we do is take the voltage, and that's going to be equal to the current times the resistance. And so what's our voltage? You can see it's 9 volts. What's going to be our current? We don't know. That's an unknown. And what's our resistance? It's 10 ohms. And so if I put a 9 here and a 10 here, dividing both sides by 10, I should get a current of 0.9. So let me connect that and make sure that we're right. Like that. So it's 0.9 amps. And so that's a pretty simple simulation. Now let's figure out what happens when we get rid of that resistor. So I'm going to remove that, and then we're going to add a capacitor to it. And so what I want you to do is when we connect this capacitor, and remember, using our analogy, a capacitor is going to be like a dam. So what I want you to do is, as I connect this capacitor together, watch the amps right down here. And so as I connect that, you could see that it briefly goes up. So there's a buildup of current, but then it stops. And that's because we're building up charge along each of those plates inside that capacitor. And so in electric circuits, you're going to have circuits that are either in series. In a series circuit, one element just comes after another. So one after another after another. And then in a parallel circuit, we're actually going to have a number of different circuits that are connected together. And so you should be able to understand what happens if I add a switch right here in a series circuit. Well, think back to that flow of water. Since the water can't get through here, it's not going to be able to get through the whole thing, and so there's going to be no current in this whole circuit. What if I move it over here, or what if I move it down here? It doesn't matter. In series connection, if you ever have a switch in the middle, the whole thing is going to stop. And that's just like those old Christmas tree lights where one bulb would go out and all of them would go out. So in a modern Christmas tree light string, they're not going to be connected in series, they'll be connected in parallel. And so watch what happens if we add a switch right here. Well, there's not going to be flow through this side, in other words, this side of that parallel circuit, but we're still going to have current through here, and we're going to still have current through here. What if we were to add it there? Well, we're not going to get return on these two, but we're still going to have flow through here. Or if we were to add it just to that one element, we're going to have flow or current through these two over here. So understanding how a series is different from a parallel circuit, and it can get more complex than that. And so now I've connected a number of different resistors in series, and what we're going to look at is their voltage. In other words, that potential difference and then the current. And so you can see that I've connected it to a 9-volt battery. And now I'm going to move that voltmeter, and you can see that the voltage across those resistors, right there, or that one resistor, is 3 volts. If I move it over to this one, it's going to be 3 volts. If I do both of them, you can see it's going to be 6 volts. And so really what we're doing is we're dividing that voltage across all 3 of those resistors. But now let's look at these 3 10-ohm resistors. Could you predict what's going to be the current through the circuit? So just like we did before, Ohm's law is going to be helpful. And so what's our voltage? Our voltage is going to be 9 volts. What's going to be our resistance? Well, let's make this easy. Since we have 3 10-ohm resistors, what if it's 30 ohms? What if we can simply add those up? So if we put a 9 here and a 30 here, let's watch what we get. We're going to get 0.3 amps. And so Ohm's law works in this case. And so when you're connecting a bunch of resistors in series, you simply add the resistance of all of those resistors, and that's going to give you the overall resistance. It doesn't matter where I put that ammeter, it's still going to be 0.3 amps. And that's, going back to the analogy of water, all the water is flowing through that circuit. So now I've connected a bunch of resistors in parallel. And let's look at what happens to the voltage across each of those elements. So if I put the voltmeter here, it's 9 volts instead of 3 volts. Or if I move it down to the next element, it's still going to be 9 volts. Or down here, it's going to be 9 volts. And so it doesn't matter. In a parallel circuit, it's going to be the same voltage or same potential across all of those. Now let's look at the current. So we're going to use an ammeter. Before, remember, with those 3 10-ohm resistors, it was 0.3 amps. But let's move this ammeter around and see what we get for current. So here it's 2.7 amps. If I move it down here, it's going to be 1.8 amps. If I move it down here, it's 0.9 amps. And so I'm getting different current in different parts of this electric circuit. And so that's a little bit confusing. And so if we go through circuit arrangement, if we're looking at resistors connected in series, the resistance is simply going to be the summation of all of the resistance of all of those resistors. And so since we had 3 10-ohm resistors, we just add those up. So we'd have 30 ohms of resistance in that whole circuit. Then we can use Ohm's law to solve the problem. So if we're to measure the resistors in parallel, it's going to be a little more complex, where 1 over the resistance in parallel is equal to the summation of each of those elements. And so 1 over the resistance in parallel is 1 over 10 ohms plus 1 over 10 ohms plus 1 over 10 ohms. And so that's 3 over 10, and I could solve my resistance in parallel as 3.33 ohms. And that's why when we have all 3 of those together, we get 3.33 ohms. And when I figure out my current on a 9-volt battery, it's going to be 2.7 amps. And so did you learn to make predictions of the changes? So as we move elements around, how's that going to affect a circuit? And then could you plan to collect data? And so again, I'm using a PHET simulation. I'll put a link in the video description down below, but I hope that was helpful.